What up, guys? So 11.4 is going to be all about chords. We've already talked about different parts of a triangle. We've talked about the angles and how to find arc measurements and all kinds of things like that. Today we're going to talk about the chords. Recall from 11.1, chords are line segments that go from one side of the circle to the other, and their ends are on the circle actually. So first we're going to start off with a diameter chord theorem. And it just states, if a circle's diameter is perpendicular to a chord, then the diameter bisects the chord and bisects the arc determined by the chord. So here's what this says. We know that AD needs to be a diameter. So this is going to be a diameter. So it goes through the center from one side all the way to the other. So it's a diameter. If that is true, and we have another chord, which is right here. So EC is just a chord. Line segment EC is a chord. Okay, that's all the ifs. So if we have a diameter, we have a chord, and it's perpendicular right here. I showed that it's perpendicular. Then here's what I know to be true. It bisects the chord. So that means that this is bisected. So that bisect means cuts evenly. So I know this. So I know that EB, that line segment, is congruent to BC. That's the first part. And it bisects the arc determined. So this arc right here, which is this arc right here, would be cut evenly so that ED arc would be congruent to DC arc. That's all that theorem is stating. There's going to be a proof. You're going to have practice examples, obviously, in the skills using that, where they're going to give you this part right here. You're going to figure out this, or they'll give you this whole thing, and you're supposed to figure out this part right here. So that'll be in your skills practice when you work on that. But here's a proof, and I wanted to give you some more examples. It's in page 879 of your book. They give you the all black, all the red is what's the answer, and I'm going to go through it with you real quick. So first, we are proving this theorem to be true. We are proving that when you have a diameter and you have a chord and they're perpendicular and they intersect, that it's going to cut it in half. So here's the way that you're going to do that. So given that this is a diameter, so we write that down first. That's the first step. And we also write that this is perpendicular, which means it intersects at 90 degrees. The next thing that they have us do is connect O to D, and all you're doing is when you're doing that, when you connect that right there, hopefully you realize that's from the center to the outside. These are radius, so these are just radii. All right, so it says that angle OED, this angle right here, is 90 degrees, and we know that because it's perpendicular. We also know that's 90 degrees, and that's because definition. Wow, my fault. That's because definition. There we go. Definition of perpendicular lines. We know that these are right triangles. That's because that's the definition of right triangles. So we've established that we got right triangles. We know that segment OD is congruent to OA. So OD is congruent to OA. And why do we know that to be true? Because all radiuses or all radii on the same circle are congruent. We know that to be true. We know that OE is congruent to OE. So this line right here that they're sharing is congruent to itself, and that is the reflexive property. Again, this is a proof. Now, you can use what they use. They use HL theorem, but again, we really could have used on this one, we could have used, we could not have used anyone. We had to use HL theorem because we have a hypotenuse and we have a side. That would be angle side side, which we don't have one of those. That's why we have to call it HL. And then they say, basically, we know that ED is congruent to EA. This right here is congruent to that. And why do we know that to be true? Because of CPCTC. And we want to show that it bisects it. Well, we know that this bisects it because that's the definition of a bisector. So we proved that's one of our things that we wanted to prove. And then they know that this is congruent to that. So we know that DO DOE. DOE is congruent to AOE. We know this is congruent to this, and the reason we know that is, again, corresponding parts of congruent triangles congruent, and we know that this has to be the same, and that's because of congruent central angles, and then boom, we've got this bisects it, and that's the definition of a bisector. So that's the proof that shows whenever you have a circle, you have a diameter, and you have any chord, that it's going to bisect this, and it's going to bisect the arcs. That's all that proof was showing. All right, equidistant chord theorem states that if two chords are of the same circle or congruent circles are congruent, they are equidistant from the center of the circle. So here's what I have. I did this with two different ones because I wanted to show it could be two chords of the same circle or two chords of congruent circles. So we have these two circles are congruent to each other. And what this states is if you have two chords of the same circle that are congruent, so this chord right here, so we'll call this AB, pretty much given to us as AB, that chord is the same length as, we'll call this DE. We know that to be true. That's the if part. That says two chords of the same circle or are congruent. So we're saying these two are congruent. That's the first stipulation. Then they're equidistant from the center. So that means that this distance right here is going to be the same as it is over here. And that doesn't matter if I had something like this happening where it's on the same circle and I have F and G, and FG is the same length as AD. I know that this distance from here is going to be the same also. And I know that doesn't look right, but just showing both. Here again is a proof. I'm just going to kind of go through this. Again, we know that all of the radiuses are the same, so they drew these radii on here. And boom, I showed that these all four, which makes that an isosceles triangle. When I make that isosceles triangle, I know this is the altitude and this is the altitude, so they're going to use those things down here. So just remember those as you're looking through this proof and see if you make sense of why these things are true. I just put this up here for you to kind of look through. You might want to pause the video and go through it. As you're going through it, if you have questions, again, you can come see me in class and ask me a question about why this proof is true. Just another example of something that you need to get to understand for the EOC. There will be proofs on these guys, and you're going to have to come up with them on your own. So the more you see them, the better you're going to get at them. All right, equidistant chord converse. Converse is when you switch it. The last one stated that if I knew two chords were congruent, so the last one said you got a circle, you got two chords, I know these guys are the same, and then I know that they're equidistant from the center. The converse would be to switch that, right? It would say if two chords of the same chord are equidistant from the center, so I know this to be true. Those two guys are congruent. If they're the same distance, then I know these two chords are the same length. Remember, you're going to have all these different theorems that are going to be all mixed up. The only way that you are going to get them down, make some flashcards, go over them so you don't mix them up. Again, another theorem. The congruent chord arc theorem states if two chords are the same of the circle or congruent circles are congruent, then they're corresponding arcs. So here's what this says. If I know these two chords are the same, and I know this circle right here is congruent to this circle, then I know this arc is going to be same as this arc right here. So that, just to get some stuff right here, it would be EF line segment is congruent to HJ. If that's true, and these circles are the same, we'll call this circle A, we'll call this circle B. So circle A is congruent to circle B. If all this is true, then what I can say is I know that arc EF, that arc, is congruent to HJ arc. All right, last theorem. So segments of chords are the segments formed on chords when two chords intersect. So right here, you've got two chords that are intersecting each other. This right here would be considered a segment of a chord. This right here. This right here is a segment, this right here is a segment, and here's a segment. So we got 4 segments up there. The segment chord theorem states that if 2 chords of a circle intersect, then the product, multiplication, product, of the lengths of the segments of one chord is equal to the product, again multiplication, of the lengths of the segments of the second chord. So all this is saying is if you take yx, the length right here, and you multiply it by xw. So all you did is you took this length right here, you multiplied it by this length right here. It's going to be equal to, if I took zx, this line segment, and I multiplied it by xu, this right here, those two things are going to be equal to each other. That's all that theorem is stating. Again, when you get into the skills practice, you're going to be using these theorems. So first, tonight, make sure you understand the theorems, highlight them, go over them. Each one of these is in your book, by the way. All I did for this right here is I just copied and I pasted this in from your book. This is also in your book. Any of those things that have that bold in it, they're going to be in your actual book. You can write those down on flashcards or anything, but really need to know your theorems. That's what's going to help you solve for X or find the length of a chord or whatever you are asked to do tomorrow or the next day on your skills and on the tests. So have a great day, guys. Appreciate it.